Without further ado, please take it away, Ben.
Great. Thank you for the introduction. Somebody walked into this room wearing this giant Wi Fi pineapple on their back. Most people would probably think that connecting to a VPN server would protect them from the machine in the middle attacks that they would be subject to from this adversary. They might also think that as long as the attacker doesn't control the VPN server, and as long as they don't control the path in between the target and the VPN server, that they're also safe from the machine in the middle attacks. What I'm going to show you by the end of this presentation is that an attacker having nothing more than a VPN client can actually successfully execute machine in the middle attacks. This is a pretty serious threat, particularly to at-risk groups like journalists and dissidents, because it effectively increases the attacker's range, uh, taking them from an adjacent position to in path. I'm going to use the following example to describe some of the previously documented attacks against VPNs, the attacks that we consider, and then demonstrate how we can leverage the VPN client to escalate to an in-path position. Suppose that there's a Canadian journalist living in the UK and connected to a VPN server in France. There's multiple pretty well-documented attacks against the client side of the connection. Ramesh et al. Documented a pretty thorough analysis of the server side of the attacks against the server side of the connection. And Tully et al. Identified some injection attacks from an in-path adversary between the VPN target and VPN server. But these attacks all have the limitation that the attacker basically has to directly target either end of the VPN connection. An adjacent adversary at the network level, by contrast, is obviously not in control of the connection at that level, but there's only been one attack with an adversary in this position that we've been able to find. This is the exact position that we assume for our attack scenario, where a attacker and a client can connect to the same VPN server, but that's the only hard requirement for our attacks. This is consistent with modern VPNs that are currently marketed to consumers for privacy enhancement, like Express or Nord, for example. I'm only going to cover the two attacks that I think represent the biggest threat, and I think demonstrate the capabilities that we're going to show you today. The first is called the ATIP, or adjacent to in-path attack, and as the name suggests, it allows an adversary to escalate from an adjacent to in-path position. The next attack is called the eviction reroute attack, and it allows an adversary to redirect packets intended for a target to the attacker instead. Oops. So before I cover that, I'm going to discuss the VPN connection process and the IP obfuscation process a little bit, and in particular focus on the connection tracking framework, because that's where the vulnerability that we identified lies. So when a client connects to a VPN server, it sends a packet to the VPN server's listening port 1194. The VPN server is obviously then going to respond with some configuration information, including a private IP address for the client. That connection is stored in a global shared table circled in red. There's two pieces of state stored about each connection. One is the originator information, which is the connection tuple in the client to server direction. The second piece of information is basically the same information, but it's the source and destination ports and IPs are flipped, and that's for the reply direction or server to client. So now suppose that a client is going to send a GET request to a web server. The packet first gets sent to the VPN server. The VPN server's connection tracking framework then rewrites the source IP address of that packet from the private IP address of the target, which in this case is 10.8.0.7, to the VPN server's public IP, 2.2.2.2. That's basically how the VPN uses the connection tracking framework's network address translation capabilities to implement IP obfuscation. And so the VPN, the web server is going to send a packet back to the VPN server. The VPN server's connection tracking framework is going to intercept the packet, and then make sure that it gets routed basically back to the client who connected to the VPN server. So now that I've covered those prereqs, I'm going to demonstrate how an attacker having nothing more than a VPN client and connecting to the same VPN server as a target can escalate to in-path. So assume that the attacker is connected to the VPN server, but the target is not. The attacker is going to send a packet through the VPN server to the target's public IP address. The important detail of this packet is that the source IP of the attacker's packet is equal to the source port, the listening port of the VPN server. What this does is it creates a collision for any incoming packets towards the VPN server. And so if you notice, the connection, the entry circled in red has this property where there's the private IP of the attacker and then the attacker, the VPN server's public IP or public port. So now assume that the victim tries to connect to the VPN server. If the VPN server is secure, it's going to process this VPN connection request directly. Unfortunately, what we found was that in the case of Linux and FreeBSD, when it receives a packet that was sent in this way, where there's a port collision, the packet's routed to the attacker or to whoever inserted that packet, right? We call this attack primitive the port shadow, and it underpins the remaining attacks that are covered in the paper. So once the attacker receives this second packet, it's going to repackage it and act as a second NAT, and it's then going to forward it on to the VPN server as if it's establishing a second VPN connection. The VPN server is then going to obviously store that information in its connection tracking table. It's going to reply with connection configuration information to the attacker. The attacker is then going to take this response, this second VPN connection, and it's going to send it through its first tunnel. And then the VPN is going to forward it back to the attacker. So from the target's perspective, the connection is established as normal, but in reality, the attacker has escalated to an in-path position. So normally when a attacker or when two clients connect to the same VPN server, the topology is going to look like the top figure. But after successful ATIP, the attacker is in-path. So that's the first attack. I think it's pretty cool. The second attack is called the eviction reroute. Let's go over that real quick. Assume that the attacker and target are connected to the VPN server. And assume that the attacker is between the VPN, the target and the VPN. The attacker is going to send a large volume of packets through the VPN. These packets are basically arbitrary, and they're only intended to consume space in the connection tracking table. The target, assume it makes a DNS request. The VPN server is going to store that connection information in the connection tracking table, of course, and it's circled in red. And if you'll notice, the source IP in the originator direction is the VPN, is the target's private IP. Because the attacker is in path, it can sense this DNS request based on the packet size. What it does next is send another round of packets through the VPN server. And that causes the VPN server to evict this entry from the table. So now you'll see that the entry is gone. The attacker then replaces the target's DNS entry with its own. And if you'll notice, now the source IP in the originator direction is the private IP of the attacker. So when the DNS server finally does respond to give the target whatever DNS information it needed, that packet gets sent to the attacker instead. So a successful eviction reroute basically looks like the bottom figure where the target or the victim makes the DNS request, and then the packet is actually diverted to the attacker instead. We tested all of these attacks against Ubuntu and FreeBSD. In general, the ATIP worked in all cases, There are some logic issues on the FreeBSD side that make some of the attacks difficult or impossible to conduct. But the most serious attack, the ATIP, is possible in basically all cases with some caveats that are covered in the paper. This is ultimately the result of 5 shared limited resources that we identified, and this is kind of the analogy to the Wi-Fi pineapple. You're sharing a Wi-Fi connection, right? That channel in the Wi-Fi pineapple case. In the VPN case, you're sharing the VPN server and all the resources that come along with sharing that resource, right? So that's ultimately what the cause is. We proposed 6 mitigations. We were able to test 5 of them in multiple different contexts, and we followed a 45-day ethical disclosure period consistent with U.S. CERT. This vulnerability was assigned a CVE 2021-3773. The developers were the VPN on the VPN side. The developers, it's like this is kind of not our code. That there's not a whole lot they can do. On the OS side, the workaround is to basically use firewall rules. And there's details in the paper that will hopefully explain that, and I can answer questions related to that if needed. And funding, of course, and questions.
Thanks, Ben. Any questions? Please raise your hand so people with the mic can find you. Always on the opposite side of the room somehow. Let's take this one first, if you don't mind.
So, a quick questions. How easy it is for the adversary to populate the shared table? I assume there was a limit given a given client, right?
So the limit depends, at least in the case of Linux, the Ubuntu, sorry, it depends on the amount of RAM. It's not that hard though. I'm kind of glossing over some stuff, but you can fill the table up pretty fast, in under 5 minutes or less. For the ATIP, it's like 100% successful.
Oh.
And so
Cool, thanks.
Hey Ben, awesome presentation. Thanks for your work. Curious about challenges you might have had across VPN implementation. So my initial intuition was that, at least when I first thought about it, that this would be much more difficult with WireGuard because of the way they silently drop traffic and the way that the public keys work. But so I'm just curious if you had challenges between like OpenVPN, which was the example that was prominent in your presentation, versus like a WireGuard implementation.
not really. I think is the ports. Okay, the port numbers is cool. It actually in some way might here for WireGuard because like if you all the example configuration is like a very high number port, and so for FreeBSD, so there's a restriction on the random ports that you can actually use. And so it actually in some ways might be here for WireGuard because it just depends on what they do, but it's actually not worse. It's not more than the part. Yeah. So, but I can.
Okay, thanks. In the interest of time, let's thank Ben again.